Hi, so as an appendum to the video we've just done on Astar search, how the search strategy works, and many of the key ideas and heuristic properties that are necessary in order to guarantee its performance, what we mentioned very briefly there is that Astar is optimally efficient. So in this small video, I want to do a very quick dive into what this actually means and why this is such a really, really powerful and important characteristic of the algorithm. So interestingly enough, right, the Astar algorithm was developed all the way back in 1968. So it's been around for a very long time in the literature, and it still holds its own in terms of the state of the art, despite the fact we have built things to improve upon it. Astar remains a very, very prominent staple in the area of heuristic search. And so part of the reason why that is true is this concept that Astar is optimally efficient. So what we're trying to say here is that there can exist no other algorithm A, we'll call it algorithm A, not Astar. There can exist no other algorithm A which is less informed than Astar, right? So in the sense that it doesn't have the same information as Astar, it cannot possibly expand fewer nodes than Astar, right? So that is an extremely powerful guarantee. We're saying Astar is this gold standard of the work we're going to do. In other words, what we're saying as well is that the search strategy of Astar is the best we can get. That is exciting. Now, I think what naturally then follows is the question you all may have now. Okay, if Astar is amazing and optimal, how are we ever improving on Astar? How has the state of the art pushed this algorithm further? So I'm going to do another quick video after this one where I do a deep dive into the actual ways you can improve the algorithm. But what's interesting in that discussion is the idea that you improve Astar through additional reasoning and pruning of the search space and abstraction and other things, targeting other aspects of the problem that we can improve that are not, or that is not, the search strategy itself. So we can rest assured that Astar has the best search strategy, this F equals G plus H. And so I'm going to write up the statement I said before, and we're going to write a very quick and easy proof by contradiction such that we can prove this statement is correct. Okay, so I've written up the statement before. There exists no algorithm A which is less informed than Astar, but which could possibly expand fewer nodes. We're saying Astar is optimally efficient. It is expanding the fewest nodes. No strategy that is less informed can expand fewer, right? If we are more informed than Astar, if we have a better heuristic, of course, then you can expand fewer nodes than Astar, right? Like we've already seen that the better our heuristics are, the faster search is, and then the more accurate it can expand correct nodes. But of course, right, if you had a better heuristic, if you then swap that out and put that exact same heuristic into Astar, Astar is going to do the optimally efficient number of expansions. Now, what's really important is in this statement is that this only holds up until tie breaking, okay? Holds up until tie breaking. So what we mean by that is when we're talking about the number of minimum expansions of nodes with different F values, right? In the case that your search frontier has a whole series of nodes with the same F value, well then the number you need to expand may vary based on your tie-breaking strategy. So if you had a random tie-breaking strategy, of course some runs of the algorithm may expand fewer nodes than others because you just happen to stumble onto a more promising node. But in the situation that we have a deterministic tie-breaking strategy, right, we select the same one every time, well then we again have this situation. So we're only talking about optimal efficiency in terms of our search strategy, right? The order we choose to expand nodes, And all algorithms also inherently have this idea of a necessary tie-breaking strategy, and this is something that is important to take into account, but we're reasoning over the things we can control, right? Our ranking and selection of nodes. So this statement holds up until tie-breaking. Okay, so what I want to do over here then is to step through what is essentially a very simple proof by contradiction to try to convince us all that this statement is true and that this property holds. So let's first when we do a proof by contradiction, we have to make an assumption, right? So let us suppose that an algorithm A is less informed and expands fewer nodes than A star, right? So we're starting by assuming, hey, this is false. We're assuming the opposite. And we're going to prove, well, by contradiction, that can't possibly be the case, and therefore this statement must be true. So let's dive into that. Now, so what we're saying is that in our proof by contradiction, we're supposing that there exists an algorithm with a heuristic h1 that is more clever than A star with a heuristic h2. So we're saying, hey, let's suppose the idea that there is a better algorithm than A star. It has a different heuristic h1, and the heuristic is less informed, right? So h1 is less informed than h2. So because of the fact that we're saying that the other algorithm A of h1 is more clever, right? It's going to expand fewer nodes than the A star algorithm. Well, it follows then that this means there exists some node n where this second heuristic h2 in the A star algorithm, it is giving a lower f value, right? We're saying, hey, this is a node that we, the A star algorithm, thought was necessary to expand, whereas the other algorithm didn't need to. So essentially, if I write that mathematically, then we're just saying that the f value of some node n, according to the heuristic 1, well, this has to be greater or equal to the f value from our A star algorithm. Okay? This comes from the idea that, hey, this was the node that A star had to expand, that the other algorithm, being more clever, got to ignore. So what this implies, essentially, right, our heuristic h1 was more informed than the heuristic h2. Okay, so that means h1 of n was also greater or equal to h2 of n. Right, in order for the f value here to have been rated differently, well, we're saying that the f value was less than some other algorithms A's, and because of what we're essentially saying in this situation, the heuristic had to be more informed, right? So essentially what we're saying is that, well, A, from our initial supposition, right, that the heuristic h1 is less informed than the heuristic h2. However, from this statement here, we're saying the f value of h1 was greater than the f value of h2. Well, okay. This then suggests, it implies directly that the heuristic h1 of this node was greater or equal to the heuristic estimate of h2 for the same node. Otherwise, it doesn't follow, right, that the initial f of h2 was the smaller or equal value. So we've derived this implication, but then hang on, let's consider again our original supposition. Right? So we're arguing that h1 is less informed than h2. Okay? Well, here directly we've just said that h1 is obviously more informed than h2. h1 is giving us different information than our obviously incorrect, our worse heuristic h2. Well, this is a contradiction from the get-go. And so I'll write that down. Right, but h1 was meant to be less informed than h2. Therefore, this is a contradiction. Ta-da. So it's a very simple proof, but otherwise I think this is a fairly way to show, hey, look, the A star algorithm is optimally efficient, which is really exciting. But yeah, but we do seem to have these open questions of, well, then how are we going to improve upon the Astar algorithm, which, as a spoiler alert, we absolutely do commonly in all of the state of the art in the area over the last X number of years, right, since 1968. So please stick with me in the next video as we discuss how can we improve the Astar algorithm. Thanks.